So we are starting the next section, which is about related rates of change. We already know that derivatives are rates of change, and in this section we are going to see how different rates of change are related. So let's start with this example, example 1, which is actually a question: how rapidly will the fluid level inside a cylindrical tank drop if we pump the fluid out at the rate of 3000 liters per minute? So we start the solution like this. We draw a small figure, which is not geometrically accurate. It will just give us an idea of what's going on. So this is the cylindrical tank. It has some radius, and by naming these things, we start the solution. Let the base radius of the tank be r meter, say. M stands for meter. And let the volume of the fluid in the tank at the time instant t minutes be V cubic meter, because we are considering the unit meter for radius, so we express the volume in cubic meter. Let it be V. And at that same time instant, let the height of the fluid surface be H meter. You can understand that as fluid is being pumped out of the tank, the volume is decreasing and so is the height. The rate of decrease of volume is given. It is decreasing at the rate of 3000 liters per minute. So we have to calculate the rate at which the height is decreasing. But radius, of course, does not change. And these quantities, of course, are related by this equation: V equals pi r squared times H. Note that V is not the volume of the entire cylinder. V is only the volume of the fluid at any given time instant t. But because it's inside this cylindrical tank, it also assumes that shape. That is why it's related to these quantities like this, using the volume of a cylinder, that formula. Now next, of course, what we are going to do is we will differentiate both sides with respect to t. For that, we are going to assume that both V and H are differentiable functions of t, which of course we have to assume. And doing the differentiation, we get this, which is a very simple thing: dv dt equals pi r square times dh dt. R square does not change, it just stays r squared because it's constant, it's not changing with time. Now this is given to us that the volume is decreasing at the rate of 3000 liters per minute. Because it's decreasing with time, so we have a minus sign here. But the volume is not expressed in liter. We have chosen the unit cubic meter for volume. So you need to convert this liter into cubic meter, for which you have to divide by 1000. And that's how you get this figure. So we now know this, we have to calculate this. And then using this value in this equation, this is what we get: minus 3 equals pi r squared times dh dt. From which we solve for dh dt and we get this minus 3 divided by pi r squared, which we can express in words like this. Thus the fluid level is dropping at the rate of 3 divided by pi r squared meter per minute. So you can clearly see that the answer depends on the base radius, obviously. But you notice one more thing from this rate, that is how it depends on the radius. If your radius is large, if the tank is really large, means it's really wide like this, really wide, then the ratio is small. That means the level will drop more slowly. Whereas if you have a small radius, if your tank is more like a tube, then the level will drop rapidly, provided you keep this rate at which fluid is being drained out of the tank constantly this 3000 liters per minute, which also matches with our experience. If the tank is really wide, then it will drop more slowly, whereas if it is narrow, it will drop more quickly. There are, of course, other examples in this section that you study yourself. Actually, there is nothing new in this section for us to learn. All we do is we use derivatives and what we know about derivatives to solve problems like this. So instead, what I will now do, I go straight to the exercises and I'm going to solve only this one. There are many exercise problems. All of them are left to you except this one. So this is number 2. Suppose that the radius r and surface area s of a sphere are differentiable functions of t. T denotes time. Say with time these things are changing in some way. And you also know that if r is the radius of a sphere, then its surface area is 4 pi r squared, which the authors are calling s. We have to write an equation that relates these two rates, ds dt, the rate of change of surface area with respect to time and the rate of change of radius with respect to time. So here you can see, just like you saw in that one, that two rates are being related. In other problems, you will see that more than two rates will also appear. So the solution is just this, that you have to differentiate both sides of this equation with respect to t. And for that, you also need to apply the chain rule, the usual stuff. So the left hand side will be ds dt. Because 4 pi is constant, it will first come out of the differentiation process by the constant multiple rule. And then you differentiate r squared, but with respect to t, keep that in mind. And this is where you have to use the chain rule. And that's how you get this. First you differentiate r squared with respect to r, obtaining 2r, and then you multiply that with the derivative of r with respect to t, dr dt. So that's how you get 8 pi r times dr dt. This is an equation which relates these two rates.